Okay, so hi all. So in this video, I'll finish up with the notes and examples on recursion, and we'll do a little bit of coding together to get a base program off the ground, which as usual will probably be useful for you to use as the starting point for the next lab, which is posted on Canvas, and you'll be working on over the weekend to hopefully have your first try at writing some recursive functions of your own on just a simple linked list, since we're already pretty familiar with that, hopefully. So I won't go through all the notes from last time, but we'll stare at one program that we wrote last time. Was just a basic printing function. So, of course, what's the idea of recursion? So the idea of recursion, or a recursive function, is that the function is going to call itself. So as you're executing the function, you get to a point where perhaps you decide, oh, I'm going to call this print function again. And the idea is that, of course, much like many things we've done in programming, you need to be able to repeat stuff. Now, of course, maybe we've gotten all nice and warm and cozy feelings about loops, which of course do a great job of letting you repeat a chunk of code as many times as you want. So recursion, at this point at least, is just an alternative to doing loops. And there's still plenty of times or instances where a loop is probably what you're going to use, and you're not necessarily going to use recursion every single time. But we will eventually get into some cases where we really actually need recursion, because loops aren't going to quite do the trick because of the nature of the way we're moving. But we'll get to those. But for now, at least, we did a translation, I think, last time of just our usual printing loop and turned it into a printing function, a recursive printing function. And of course, nowhere in this code right here do you see a loop. And yet, we all know, of course, to print out a linked list, you obviously need something that's at least acting like a loop in order to say, print the current number, go to the next one. Print the current number, go to the next one, right? That's a loop, of course. But we can accomplish a loop by essentially, instead of saying, oh, hey, go back to the top, well, that's essentially what this does, is it says, oh, I call the function again, which is, of course, going to essentially have you go back to the top of the function and do it again. All right, so we did that example, and I think we left off on this one that we did, which is maybe adding numbers up in a linked list and returning the sum to the main. So for sure, if we have a return involved, I think this is where we left off last time, a good thing to take note of is that if you're going to do some action that requires a return back to the main, so let's say, I'm going to print out the result of that, for example, then what's the idea? Well, of course, I think we correctly wrote some nice code to keep track of the sum, to keep a running total. Remember, of course, also, I pretty much never want to make local variables inside of a recursive function, because, of course, you're going to be declaring them every single time you call the function, which is many times. Instead, if there's something you want to keep track of, make it a parameter. So in this case, I want to keep track of what's the sum so far. And so I made that a parameter to the function so that when I start from the main, I could send at 0, which is going to store 0 in total. And then as I accumulate and update total, since I'm calling the function every time, the updated version of total is going to get sent in, which means by the time I'm done, remember that's the base case, is when we say, you know what, stop and send, in this case, send your answer back. When it's finished, I know that when I get to this case where I am done, I know the total will have been updated however many times it needed to be, and that will be the value that I want to send back. So I think at the end of the last video, I threw in this extra, what maybe seemed like an extra return, in order to be able to establish this sort of chain of passing the solution all the way back to the main. Now, I said that at the end and probably didn't justify it very well. So the next couple of slides here are going to expand upon that a little bit and show you what I mean by that. So if that last part of the last video didn't 100% make sense, stay tuned, because we're going to do a little bit deeper analysis of what's really happening here. So in order to better understand that, right, and this sort of flow of how the processes work and all of that, we do need to take some time to think about and chat about what's known as the runtime stack of your computer. So we don't talk a whole lot about these kinds of things in this class. You talk about it in some others, but what's actually happening in your computer when you in your computer sort of to-do list, right? So I think we all have an idea that a computer is something that when we use it, we're telling it to do a bunch of tasks, and of course it's doing them. But in reality, those tasks, or jobs as they're usually called, that we send to our computer, there has to be some organizational structure to them, because otherwise how would it know which one to do first and second and third and so on? And part of the reason why we learned about stacks is because the way that the computer organizes its tasks is in a stack. Remember, of course, the idea of a stack is that new things get placed on the top, but things that are getting removed also get removed from the top. And that's actually how a computer organizes the jobs that it needs to do. And that stack is known as, formally, as the runtime stack. And sort of, you could say the computer has a runtime stack, or any process that you're running, like, for example, your program that you're writing, has a runtime stack or a stack associated to that is sort of a jobs list or a tasks list. But it is a stack. I'm going to keep saying that word stack over and over again because it actually matters that it's a stack instead of a queue, because it influences how all this stuff's going to work. And this is intimately tied into why recursion actually works. All right? So let me describe this in a little bit greater detail, right? So when a job is generated, of course, for us being users of a computer, that's usually us telling the computer, hey, do something. Go print this thing, or go to this website, or whatever, right? So when a job comes into the CPU, it is literally pushed onto the top of the runtime stack. So of course, if there's nothing there, it's going to do it right away. But if you got a bunch of jobs already in the stack, it's simply going to push it onto the top of the stack. All right. And of course, when the computer goes to actually execute a job, because it says, okay, I'm free, I'm ready, I can do whatever you want me to do, it's going to pop the top job or task off the top of the stack. So, okay, this maybe seems like I'm making a big deal out of nothing. Fine. So as a regular sort of flow of jobs, I might, as a user, have these 3 jobs for my computer to do. Go to a website, download a document from that website, and then print that document. And of course, as a human, quite literally, as I'm clicking to say do these things, I am probably sending these jobs in the order that they're listed. Obviously, first I go to the website. Second thing I do is maybe hit the download button on that website. And then the third thing I do once that document opens is I hit the little print icon in order to print it. Right. So of course, this isn't a very exciting example, but I'll draw it for you anyway. So if here's the runtime stack, I'm going to do it this way so I don't have a lot of space here. Then of course, what if I do them in this order, if they come in this order, right, then first I go to the website. So I push that onto the stack. So I push a little job, which we'll do as a rectangle, which is go to web. So I do that, right? I type in the website or whatever. And of course, as soon as I hit enter or whatever, it starts processing this job. Now, of course, for the most part, it's the only thing on the stack. So I say go to some website and it says, oh, okay, I'll do that. And of course, it is able to fully complete that job. And so it says, okay, I pop that off. Next, once you're on that website, or by the time you actually get to that website, if you say, oh, you know what, there's a document here I want you to download, they say, oh, all right, I could do that. Sorry, I didn't give myself enough space to go vertical here. So it says, okay, well, the stack is empty right now because I've already done that job. So sure, I'll push you onto the stack. And I'm going to do a download. And it says, okay, can I complete that task? Of course I can. So let me pop that off and do that task. And then the third thing you asked for was to print that document. And it says, oh, okay, well, I'm free right now, and I have the document in memory, so I can do that task. and I'm all done. So of course that's like silly, right? I didn't need to draw you a picture, I don't think, to tell you or to show you how that flows. In fact, we've done these steps so many times, you don't even really have to think about it. But where this actually gets interesting and what you're going to have to do in some of these problems, especially exam questions where I ask you to do some analysis, is you're going to have to be a little bit more mindful of the fact that when we're creating jobs for our CPU or for your program to do, it's possible that the computer or your program is not going to be able to finish executing one of the jobs that it's currently working on. Now, maybe you're already seeing how this fits in with recursion, because recursion, of course, is almost like, by definition, what I just said. That when you're doing a job, so calling a function, right, or executing a function, that's a job. But of course, what's the nature of recursion is that in the process of doing a job, you call the function again, which of course sort of generates a new job before you finish the one you were currently in. So this, what I'm describing to you on this slide here, happens all the time with recursion, which is why we have to be good at understanding what's happening in order to probably be good at using recursion. So what actually happens when you have these tasks, or when you have a task that you can't complete? Well, the first thing that happens is it'll do as much of the task as it can, but it will then put that job, which is in the stack, it'll put it on hold. So it won't pop it off completely, because it can only pop things off of the stack once you've finished it. So if you have a process that's running and you can't actually finish it, it's going to just hang on there, right? You sort of say you're putting it on pause or putting it on hold. You're going to leave it in the stack, so it's still there. And since you're stuck, right, or the computer is sort of stuck, it's like, well, I can't finish this. Do I just sit here and crash? I guess sometimes that does happen. But no, what it will try to do is it'll say, well, let me go to the next job. Let me go to the top of the stack, and let me see if I can do the next job, the job that's on the top. Now, eventually, the computer will be able to do the tasks. And once that happens, right, eventually all of the paused or on hold jobs will eventually make its way back to the top of the stack. And if it can then finish executing it, it will resume, or it will unpause that. And if it can complete it, it will be popped off and move on to the next one. All right, so just as a human example, this maybe doesn't make a lot of sense just yet, but as a human example, let me take those same 3 tasks that we had on the last slide. Now, you're probably saying to yourself, there's no way that I can actually send the jobs in that order, 1, 2, 3. And you're kind of right, I think, in that I don't know that I can say, hey, print a document from a website, do that first. Second thing, download that document. And the third task is go to the website where that document lives. Now, I know, right, I can't probably physically actually send the jobs in this order, 1, 2, 3. But let's pretend for a minute that I could, right? Just so that you can sort of see what I mean by this stacking nature. So the first job that comes in says print. Right, print this document. So it says, oh, okay, all right. That's the first job. So right now I'm here, I'm on print. So the computer would say, all right, I can do some things. I can, get ready to print. I can send some, transmission to the printer to see if the printer's on. Can do all that. And then it says, okay, now I need the data that I'm supposed to print. Now, at this point, though, it might say, well, I don't have that. So let me put this on pause. I shall go with the old school pause button here. Let me put that on hold because I can't finish this task. So I'm not removing it, but I'm putting that on hold because I can't actually complete it. So then it says, well, is there anything else? Are there any other jobs that I could do? Well, maybe by then, you've pushed the second task, which is to download a document. It says, oh, okay. Maybe I can download this document. All right, so let's see. Well, I'm allocating memory to hold the download. That's great, and I'm ready to do it. Okay, and I'm gonna Oh, well, the document that they want me to download is on some website that I haven't even gone to yet. So I say, even though I'm trying to do this task right now, I can't finish. Let me put that one on pause too. And I say, all right, well, geez, my stack is getting big now. But a third job comes in, which says go to some website. So it says, all right, well, let me try that one. And finally, it says, oh, hey, I'm actually able to do this. I have my browser, and I have the address, and I go contact the website, and I start downloading the information from the website, and I push it up onto the screen, and it says, oh, this one I was actually able to complete. So I pop that off because it's finished. I am on that website. Now, what would be great, now again, as a human, I'm not quite sure that this, or in everyday computer use, I don't think this quite works. So we're playing a little bit of a make-believe game here, right? But so I pop that off. I say, okay, I'm done with that one. So the stack now goes back down and says, okay, so now I'm on here. Because, of course, remember, a stack always looks at the top. So right now, download a document is a task that's on the top of the stack. Oh, well, this was paused a minute ago because it didn't actually have access to the document that it was trying to download, as funny as that sounds. But now that this website is opened up, that has a nice button over there that has the data that you need to download, it says, oh, let me unpause, and I can actually complete that task, download that document, save it into the hard drive or wherever. And now I pop that off, and that's also finished. So now I go to see, is there anything else in the stack? And now I finally get down to this job that said, they wanted to print, but I didn't have the thing I was supposed to print, so I put it on pause. So I check again, am I able to complete this now? And it says, oh, yeah, they want me to print that document that's now actually on the hard drive. Oh, I can do that task, so I pop that off. I'll print the document. And now maybe the stack is empty, or maybe other things have come in since then. All right, so again, I know that's a little bit of an unrealistic example just because physically we can't quite tell the computer to try to do things in the in the wrong order, I guess, so to speak. But that is how it would, right? If we were able to do this, this is how it would approach these tasks. And I say this to you because this is exactly what's going to happen when we run our programs, which are going to have recursive calls and recursive functions stacking themselves up like crazy. So we are going to have to be able to do an analysis kind of like the one we just did, but it won't be made up anymore. It'll actually be sort of really what's happening. All right, so to translate what we just said into function calls and all of that good stuff, I'm just going to read this very quickly to you. So when a function is called, the task, right, of running that function is pushed onto the runtime stack. Now, of course, prior to this week, you've always been in case A, which is that anytime you've ever called a function, you haven't really thought too hard about it. You say, oh, okay, the main calls the function, it does its business, then I go back to the main, and the main goes on with its life. So you've always been able to completely execute the function, so you've never really had to think too hard about it. But we are going to constantly now be in case 2, which is where we're going to call a function, we're going to push it onto the stack, we're going to start to do it. But of course, with a recursive function, it's going to call itself, which means we're almost always going to be in the second case above, where I'm going to push another instance or version of the function onto the stack and see if I can maybe do that. So the stack is, so I'm going to, I'll do an example in a minute, right? But as we call the function, I'm going to keep stacking these things up quite literally. Now, I'm in big trouble if I never unstack them, I guess, right? Or pop them. So of course, at some point, the instance of the function that you called will actually be able to finish. Hopefully you're already thinking, that's the base case, right? So the base cases, remember what makes a base case for recursion is that you can actually do it. There is no, hey, call the function again. So at some point, as we know, since we've written a couple of programs of recursive functions already, at some point one of the base cases is true. Now what's going to happen then is that we might have stacked up 10 instances of the function via recursive calls. So what finally happens when I get a base case to be true is that one fully executes. And when that happens, you have sort of a chain reaction then of saying, like we did over here, right? When I finally was able to do the top one, the go to the website, it made doing this one possible. And then doing that made completing that one possible. And so on and so on, and so on and so forth. So we're going to end up popping our way back down the stack. And that's actually that is really the recursive process that is, I don't want to call it magic, but that's the neat part of recursion, is that you're able to then sort of work your way back down. It's like setting up a big, like a bunch of dominoes, and then as soon as you knock the first one over, when you're finished doing all that work to get it set up, they all fall down in order. Same thing's going to happen here. All right? So instances will be popped off until you get all the way back to the bottom. And the main is the origin of all of these function calls. So we're going to end up eventually then sending whatever, communicating back to the main when we're finished. All right? So let me just, as a good example of this, I'm going to do a program a function that we did in the last video, but we're going to do it in a slightly different way. So this is our summing program or function here, where we want to write code that sums up a linked list. Right, so I'll just put a little linked list on our screen here. So I'd like to be able to do something that's going to add up these numbers and send it back to the main. Okay? But I want to do it with no counter. In the one that we did last time, not that this is bad or anything, but we used a counter. We called it total. And then all I was doing each time was I was just updating the total. And then ultimately at the end of the day, I sent the total back, the correct total back. But I think I could actually do it without total at all, and instead do it this way. And this is going to show us this stack thing. So let's try it this way. So I'm going to say, well, what do I want to do? So I'm going to still think about two cases, right? One is, of course, when I get to the end. Of course, this is my stopping case. So I could print all finished if I want to. I'll leave that out just to save some space. But if I'm on null, right? So when I'm down here, what's the sum of null? Well, hopefully it's not crazy to say. Well, that would be nothing, right? In other words, how much does null contribute to this sum? 0, nothing. In fact, maybe I should have said, what if you called this function on an empty list? So what if these guys weren't even here, and you just had first equals null, which means this is going to be true? Wouldn't you want to say the sum is 0, right? Because if the list is empty, then the sum would be 0, I think, right? So hopefully that kind of actually makes sense, that if temp is null, whether it's because I've reached the end or there's simply nothing there, that contributes nothing to the sum. So let me send 0 back. On the other hand, if temp is not null, I want to do stuff, right? I want to say, oh, all right, well, I want to throw this sum. I want to add my current number into my growing sum. Now, before we used a variable for that, total, and we said, oh gosh, we said, oh, well, let me update total, let me toggle temp, and then let me call the function again. But the cool kids would be a little bit slicker about this, and they would say, well, I do want to update temp, because I do want to go to the next box, right? I do want to go to the next box so that I can move on. But what do I want to be doing each time is actually I really want to be saying, well, wherever I am in the list, let's say I'm on 10, where I appear to be right now in my picture, then isn't it true that the sum would be my current number so in our picture 10 plus the sum, I'm going to just move this down, sorry about that, so send back my current number plus the sum of the numbers starting with the one right after me. Okay. Now this is going to require a little bit of unpacking, or unstacking, as the case will be. But I'll read this to you one more time, from left to right. So what's this process? This is sort of the more advanced way of thinking about recursion, is to say, well, I have two cases here. Either I am on nothing, or either temp is at a point of nothingness, in which case what's the sum? Remember, this function is supposed to tell me what's the sum. Well, if I'm on nothing, the sum of nothing is 0. So I would send back 0. Okay, on the other hand, I might be on something, in which case, what's the sum of that? What's the answer to this question? Right, the main is asking this question, hey, could you add up all the numbers? What's the answer? Well, I think no matter where temp is, you can't disagree with me, I challenge you to disagree with me, that the answer to the question, what's the sum of all of the numbers in the list, is, well, it's me plus the sum of the numbers after me. Or you could even say sum of me plus it's me plus the sum of the numbers starting at the box after mine. That is true in English, right? I think what I just said is 100% accurate. And that would be true if I'm on the 10 box. That would be true if I'm on the 6 box. That would be true if I'm on the 4 box. Whoops. Of course, I have to be a little bit careful here because, of course, I'm saying what's the sum of the numbers beyond me? Not, of course, would this include the numbers before me? Well, maybe I'm a little bit worried about that. But let's try this, right? I'll spoiler alert and say this 100% works. But this is a little bit of the magic of recursion here. So let's trace through this. So this is a good example because it's not that complicated, but shows you sort of what I mean by the stack and what's going to happen and all that good stuff. So let's say we're proposing that this actually does work. So let's try this. All right, so when the main calls sum, in the stack, so I'm going to do the stack over here. So in the stack, I get one instance of the function. Now the main is who called this. And the main called this function, sum, and it sent it first, right? That's the value that it sends it first. Okay. So when I try to do sum for the first instance of sum, it says, all right, temp is pointing to the first box, that's 10. So this is not true. So I'm going to do the else case, which is to say, so return the result of what number I'm on right now, plus the result of that function call. So what's the main going to try to return? Sorry, let me make my box a little bigger here. So when the main calls this is the first instance of sum, of the sum function. It says, okay, well, I'm going to try to send back the result of temp's num, which is 10 in my picture, right? Temp's num, plus the result of calling the function and sending it temps next. Oh, well, wait a minute. That's me calling the function again. Pause. Oh, that's going to look like an 11. Okay, I'll just say pause. And call the function again, which is going to push another instance of the function onto the stack. Now, I'm not done yet because this is still sort of, this guy's on hold, so that doesn't get popped off. But because this function called, this case called the function again, look, it's right here, it says, oh, wait a minute, I can't finish my job because I have to wait for the result of that to be processed. Oh, okay. All right. So now, of course, the first time through, the arrow was on the 10. But what arrow do I send the second instance up here? Is I send it temps next. So now temp is going to get updated. So maybe I should leave this. We'll do this with colors here or something. So the first time I sent it that arrow, but now the second time, maybe I should actually do this in green too. So second time through, I'm sending it temps next, which is 6, the 6 box. So I say, okay, all right, so now I'm on the 6 box. All right, so I come back to the top of the function. This is still false. Maybe I shouldn't cover that up. This is still false. So I'm going to do the else case, which says, oh, all right, do a return of my number, that's 6, plus the result of calling the function and sending it my next. Oh, well, that's going to cause another instance to be pushed onto the stack. And says, oh, all right, well, now let's see. Oop, I got a little low there. Well, now what arrow am I sending it? I'm sending you greens next, which is blue. So it says, okay, I come back up to the top of the file. Okay, that's still false. So I'm going to come down here, and I'm going to try to send back my num, which is 4, plus, oh, sorry, I forgot to write pause, but okay, pause. Pause here too. And 4 plus the sum of who's after me. Okay, oh my goodness. So now I got to do, I got to do this one more time where I say, all right. I forgot to put that arrow in. I got one more color in here, I think. So call the function one more time. It says, I don't know what the answer is, so let me call the function again. Okay, and now, of course, I'm going to send it, I sent it temps next, which is now purple arrow, null. So now I come up to the top of the function. Oh, for the first time, my base case is actually true. So in the purple round, which is, I guess, the 4th round here, I'm actually able to do the return. This is going to now return 0. Okay, now as soon as this so hopefully that all kind of made sense, or mostly made sense, right? So these guys are all on pause. Sorry, I forgot to write that in there. They're all on pause waiting for the response from the previous round. But when I finally get to the purple, to the last round, where temp is actually null, this actually has a return that can be done. So this is going to be popped off. I'm going to draw a line through it in a second. And since this is a return function, it is going to send its return back to whoever asked for it. Well, who asked for this purple version was the blue version. So the return that I'm going to do, which is, of course, the number 0, where is that going to be returned? It's going to be returned back to whoever asked for it. And now, since I fully completed that round of the function, that is popped off the top. Okay, now this is going to begin the parade of popping, because now I come back to the blue instance. And the blue instance said, well, all along I was trying to return the result of 4 plus mystery. Oh, no longer a mystery. Last time I checked, 4 plus 0 was something that we know what that is. That's 4. And so now, since I have a return here, right? Maybe I should have been writing that in each time, but I'm returning this result. And now I can actually do it. So this number, which of course is 4, is going to be returned. And of course, where is it going to be returned? Well, who asked for it? Oh, green guy asked for it. Now, blue, fully completed, so it is popped off. And then it says, okay, and then of course I'm still looking at the top of the stack, which is green now. And green says, oh, okay, hey, I was trying to return. Sorry, I should have written return in front of all those. Is trying to return 6 plus what used to be a mystery, but is now not a mystery. 6 plus 4, pretty sure that's 10. So 10 is going to be returned to whoever asked for it, which of course is this guy, red guy. This was able to fully do its job, so it is popped off. And now I'm finally back down to red, which was on hold, was on pause, just like all of these. But now when I revisit red, oh hey, what's red trying to do? Red's trying to return 10 plus 10. It was 10 plus mystery a minute ago. But now it says, oh wait, I know what 10 plus 10 is, it's 20. So it's going to say, oh, I know I can finally do my job, which was to return 20. Now, who was asking for this? The main. So I can pop this off, and 20 can now be returned to the main, which means back in the main, if I was printing it or whatever I was doing with it, some parentheses first is now going to be the number 20, which of course is the sum of these numbers. Okay, so I know it's kind of a lot to take in, and it maybe seems like you wouldn't do this way. In other words, if you were writing a program to add up the numbers in a linked list, oh my God, you would not do it this way. You're probably right. But this idea, right, of doing this is actually kind of really important. I do keep previewing that we will eventually move into some things that we're going to actually really need recursion for. So having hopefully a decent understanding of it on an easy program like this, which I know this is a little tricky to follow all the way through, but hopefully it kind of makes sense. It'll take a while, right? Like I said, this is the thing that you got to see and you got to work with a few times before you get it. Now, if this return wasn't here, so I'll just play make-believe for a second here, right? Oops, didn't need to actually erase it. If that wasn't there, everything we just said would still happen, except an awful thing would happen, which is that when I'm building up this tower here, the purple, right, all that would happen, I'd get to the top, it would return 0. 0 would come back down here. And if I don't have these returns, which I forgot to actually label, but they were there the whole time, then what happens is you get stuck. You don't actually get stuck. It'll still finish the job, but it will not pass this 4 from the blue round, will not get passed back to the green round. And that 10 from the green round will not get passed back to the red, and the 20 from the red will not get passed back to the main, because you didn't establish this chain of returns. So if you forget this, which is really easy to do, and you just did, what else is there, you end up losing the chain of returns, and I believe it'll just send back a 0, just sort of as a default. So if you're finding yourself in that situation where you're like, gosh, I think this is right, I don't know why it's not sending back the right thing, it could just be that you forgot to put a return in your recursive case. So I think it is true to say that I'll leave that. That basically, in every case, I think you do want to make sure, if you have a return, if your function has a return, I can't really think of a situation where you don't want to make sure that you are returning either in the base case a value, or in the recursive case that you're returning the result of your recursive call. We even had that in our example we did last time. Okay? So let's try one more, just because, like I said, this takes a little bit of getting used to. So I'll try to do this one a little bit faster, so that we can get to a little bit of coding. So here's a function that I made up. The name of the function is function. It's not very creative. And the main sends it the number 4. And it's going to do this thing. So it seems very simple, or at least doesn't look that bad. But let's see. So let's try to analyze this and figure out what it can do. Maybe you're smart and you're already seeing what it does, but we'll see. We'll see. Oop, I have a typo. I'm sorry. That should be minus. Sorry about that. So make that a minus instead of a plus there, if you would. So let's go. Let's see what happens. All right. So the main calls the function and it sends it 4. So I'll start with my stack here, building it up. I keep giving myself not enough space. There we go. So the main called this. The value that it sent it was 4. So maybe I'll just sort of remember that or something like that. Num was 4. And okay, so what happens? Well, is num 1? Nope. Num is 4. So I'm going to do the else case. So this is going to return. I'll do it this way. I'll say num was 4 here. So what's this going to try to do? It's going to try to return 4 times, right? That's down here, right? 4 times. Oh, and now I'm going to call the function again. And the function this time is, of course, going to be sent the number 3. Oh, all right. So I call the function again. Okay, I'm just going to do this all in one color. I think it's all right. So I call the function again. I put this on hold because I can't finish yet. I don't know what function parenthesis 3 is. So I have to say, oh, well, that generates another instance of the function. And now this time, num is 3, because that's the number I sent it. Okay, so I put this on hold. I come up here. I say, all right, let's see. Is 3 equal to 1? Nope. So I guess I'm down here. I'm going to try to return, in this case now, 3 times function, and now, of course, I'm sending it 2. Uh-oh. Well, I don't know what that is, because I call the function again. All right, so that's going to inspire another instance to be pushed onto the stack. This time num is 2. Is num equal to 1? Nope. So I'm going to come down to the else case, and I'm going to say, all right, so my job is to return 2 times, right, num is 2 times. Oh, I'm going to call the function again, and now, of course, this time I'm going to send it 1. So I say, all right, well, I've got to make another instance of the function onto the stack. This time num is 1. Okay, so I come back to the top of the function. Oh, all right, so now for the first time, I don't want you to always have the impression that these things run 4 times, but both of the examples we did. But for the first time now, I don't go into the recursive case, and instead I can actually execute the base case. So I can actually now do I can actually finish this instance, because this says, oh, if num is 1, then send back the number 1. Right, that's what that says. Oh, well, that sounds like a complete thought. No, oh, wait, I got to wait for an answer from someone else kind of thing. So now is the moment where we say, I can fully do this last instance. And in particular, what did this ask me to do? It asked me to return 1. And where will that go? It will go to whomever called me. So that completely executes, and a 1 is sent back to who asked for it. Oh, now this guy that was on hold says, oh, do I know how to return the number 2 times 1? You betcha. The number 2 times 1 is also known as 2. and that's going to get returned to whoever asked for it. Now come down here and say, oh, do I know how to return 3 times 2? That's 6. Sure, I know how to send a number 6. So I'm going to return that to whoever asked for it. I completely did that task, so it gets popped off. And now I'm down to this task on the bottom and says, that's 24 there. Do I know how to send back a number 24? Yeah, I do. So I'm going to send that back. Now, who asked for this? Oh, the main asked for this. So the number 24 can be sent back to whoever asked for it, which in this case was the main. So 24 will get sent all the way back to the main. So what does this recursive function do? Some of you might know this from a math class somewhere in your lives. This is known as factorial. So 4 factorial, for example, is 24 because that's 4 times 3 times 2 times 1. Right? Not that that's important. The math thing here is not important, but the execution, right, of how this sort of flows. I think this was maybe a little bit of a better example than the last one, at least in terms of my picture over here, right? So if you're trying to, obviously, of course, most of the time, unless it's on an exam, where I maybe give you a program, a recursive function, say, hey, could you analyze this and tell me what to do? I mean, more of the time, you're just looking at a blank editor and you're like, what the hell am I supposed to type, right? So of course there is an art to this, right? And I won't lie to you that it takes a little while to sort of get the hang of this. But my best piece of advice, that if I was trying to design this and said, oh, I want a function that computes the product of all the numbers less than or equal to me, on the one hand, if I think about it, the base case is sort of like, oh, that's the one that you know the answer to. What's the product of all the numbers less than or equal to 1? It's 1. What's the product of all the numbers less than or equal to any other num? Well, I don't know, but I do know that it's myself times the product of all the numbers less than or equal to 1 less than me. So in other words, right, 4 factorial, or 4, this guy, 4, is 4 times 3 factorial. So, where does a person come up with this stuff? It's mostly in thinking that way, which will take you a little bit of time, perhaps. But it's sort of almost like a little bit of blind faith. Like, I look at this, or the one we just did, and it's a little bit like, ew. I mean, look how short these are. I mean, this is a 2-line, this is an if with a single line, and an else with a single line. And yet, it kind of actually accomplishes what we used to write with a somewhat more verbose loop. This is also just 2 lines, right? An if with 1 line and an else with 1 line. And it computes, a somewhat sophisticated mathy thing. So recursion, I think it's pretty great, but it does take a little while to get the hang of it, right? So I think this is a nice summary of some of our main points here. So I'll let you read through this. I think that's the end. It is. Okay, good. So I'll just say, here we are. So I prepared just a sample program that kind of has the functions we just did in it. I was going to fill this in with you, but to be honest, it's a little silly to do so. So maybe actually here, let me just go take 2 seconds. So I posted a program for you to look at, of course, and to use as a starting point. And it's essentially just those 2 functions that we did, and then I threw in an append function just to be able to build up a list. So let me just pull that up real quick, and I'll give you a quick word or two about the lab that you're going to work on over the weekend. So the lab is asking you to do some other tasks recursively. So here's a starting point that you can use to at least have some of the basic things that we did already in place here. So so in this program, you're going to fill in It's a menu program, sort of our usual thing. And in here, I already wrote the code to load up the first node of the list, so you don't have to worry about that. And then there's a menu that's already written that has 6 options, which are just mostly our usual things. Append to the list, print the list, and compute the sum. Now these 3 I've already included, the first 3. So that code's already in there when you go to look at this program. Append is just our usual append. There's nothing recursive about it. It's just, add to the end. Print and compute sum, those are the 2 that we just did in the notes. So I just simply copied that code over from what we did in the notes. So what you're going to do is fill in code for 4, 5, 6. You're going to fill in code to compute the largest number in the list, the linear search for a value in a list, and then swap the largest value in the list with the end of the list. And all 3 of those, I'm going to ask you to do them recursively. And I wrote the main to work, which is mainly just the menu choices and the function calls. So I'll ask you, as usual, to leave the main alone and to fill in the details of the functions. So like I said, I already filled in the append function. That's just our standard add a new box to the end and put a new number in it thing, so there's nothing exciting there. The print function, this is the one that we just talked about in the last video. It's recursive, so maybe come back to that and keep looking at that if you want a little more advice for that. And then the sum function, this is the one we literally just did, right? This is the cool kids way to do summing. All right, so those 3 are already in there, and then you're going to fill in code to do these 3 functions: largest, find largest, and return. Finder is going to be returning a true false. Is the number you were looking for in the list or not? And then again, this big swap is where you're going to try. That's probably the trickiest one, I guess. So you have to think about that a little bit. But you're going to want to figure out a way to find the biggest number in the list. That's not that hard to do, right? Use a pointer for that. And then ultimately, once you know you found it, swap that into the last node. So it's sort of like a selection sort, well, in reverse, I guess. But just one round, right? So don't worry about doing the whole thing. So take a look at this over the weekend. Hopefully you will or are in the process of warming up a little bit to recursion. It's pretty neat when you do it. So even if you just run this a few times, the program that already exists for you to start with, maybe tinker around with it a little bit, put some prints in some places just to sort of see, oh, okay, that's when it does it and stuff like that. So good luck with this. As usual, if you have any questions, please let me know. I think I put Wednesday as a deadline for this, Wednesday of next week, just to sort of move us along. There's also going to be a reading over the weekend as we will start hash tables next week, which is sort of our main topic for this unit, which will actually be more than just these little quick one-day little programming tasks. We'll sort of return more to our usual structure. So check that out on Canvas, and like I said, as usual, good luck, and let me know if you need any help.